everyone, this is Andrew O, and this is our final term project for ME160, which is a bike crank arm. A bike uses a crank arm to transfer power from the rider to drive the wheels, converting force from the rider to linear motion. The crank arm connects to a chainring on one end and the pedals on the other end. The length of the crank arm determines how much force is necessary to produce a moment to drive the bike forward. The purpose of this object is to optimize the crank arm to be lightweight yet durable. Too much weight would lead to non-optimal performance. A crank arm is usually made out of aluminum 6061 due to its high strength yet lightweight properties. The result of the design optimization aims to enhance the bike and rider's performance, which could improve pedaling speed and reduce fatigue. For this analysis, we want a maximum deflection of less than 1 millimeter and a maximum stress of less than 64.3 megapascals to avoid cyclic fatigue. We modeled this crank arm as a 3D model. We considered modeling it as a 2D plane strain model, but we decided not to due to the non-uniform thickness of the geometry. We also could not use symmetry as the loading conditions for the crank arm are asymmetric. When a biker rides a bike, the maximum loading point would most likely be when the crank arm is perpendicular to the force of gravity. The force of the biker pushing down on the pedal is added to the force of gravity from the biker's leg at the pedal, generating the maximum possible moment while reducing the force necessary for the biker to propel the bike forward. We estimated this force to be around 400 newtons. We modeled this as a bearing load on one end of the crank arm. We modeled the other end attached to the chainring as a fixed end, as it theoretically should not move. Technically, there would be moments generated from things like friction from the wheels, but those would be ignored as this is an idealized model. When meshing, we noted that more force is concentrated around the two holes as well as the divot. We added an edge sizing method to those parts to change element sizes to 1 millimeter, while the rest of the body was in 2 millimeter elements. We also used a quadratic element order with quads, as they are generally more accurate than tri-elements. And for our initial results, we had a weight of around 305 grams with a total deformation of about 0.1 millimeters and a maximum stress of 10.88 megapascals.
Okay, so for our analysis of our results, we had used a mesh of 2 millimeters so that we could get accurate results. So what we found in our results, as you've seen previously, is that we saw that there isn't any singularity, and we saw that the total deformation would converge to around 0.106 millimeters, and our maximum von Mises stress that we found from doing this on the model is that we found that the max the stress would be around 10.8 megapascals. And as you can see from the right side, we have these two graphs, and these two graphs show the convergence of these two results. And we see that they have a small change, meaning that it has reached its peak, and that's how we know that there is no singularity. So in terms of our design sensitivity on the model, we basically changed the parameter of the the dimension of the length of the crank arm from one starting at 150 millimeters to 250 millimeters, and we found that the on average von Mises ranged from around 9 megapascals to 16 megapascals. And as you can see on the graph, you can see that trend there. So yeah. So when we did our design optimization, we landed on this model, as you can see here. And the way we set it up can be seen on the left with uh, the boundary conditions being the left side where the crank ring is located to be fixed, and the right side hole to have a bearing load of 400 newtons applied downwards. Same thing as the original model. And our results showed that we had a weight of basically 198 grams compared to what we had previously. And we found that the total deflection was 0.14 millimeters around there. And then we found the maximum stress is around 17.89 megapascals. So in this analysis for the optimized case, we used the same meshing size to gain that same accuracy. And we also found that according to these two charts, we found that there are no singularities and it does peak and plateau at a point due to the change being very small. And we found that the results of this optimized model for the total deformation converges to around 0.14, as I mentioned before, and the maximum von Mises stress to converge around about 17.89 megapascals. And we see that from the original model, it is deformed slightly more with about 0.034 millimeters more than the original amount. And we see that it is able to handle higher load, the same load, but for lower weight. So yeah, thanks for listening, and yeah.